Good morning everyone, Dr. Nat here. So we are going to continue on lecture number 4, which is cache memory. Lecture number 4 or chapter number 4. So we have talked about the key characteristics of computer system memory systems. So we have different locations, the internal versus the external. We also talked about capacity, whereby we talked about the memory system in terms of how many number of words does it have, how many number of bytes does it have. And then in terms of unit of transfer, we have seen unit of transfer happening before for our QPI links and also for our PCIe, whereby the unit of transfer is DLLP, and we have seen flits, fits, and also packets, right? That was for the PCIe and QPI. But for memory system, the unit of transfer would be word and block, which we will learn about in a bit. And then for the access method for memory systems, we have the sequential, the direct, random, and also associative. And we will see that the cache is typically inclined to use the random and associative. And we will discuss why. And then in terms of performance, we can characterize the memory system in terms of its access time, or we can also call this as latency, the cycle time, which is how much time does it take to execute from one cycle to the next, and then the transfer rate, which is 1 over the cycle time. And then we have examples of the physical type, and then we have the physical characteristics, which is volatile versus non-volatile. And then we will also talk about its organization, which is in the form of memory modules. We have seen this briefly, memory modules. We have seen it in chapter 2, I believe. So in this chapter, we will dive deeper into that. We have talked about the method of accessing units of data, and we have the sequential access, we have the direct access, the random access, and also the associative access. So sequential access, the memory is organized into units called records, arranged sequentially, hence the name. Then we have the direct access, whereby individual blocks or records have a unique address based on physical location. So you can the memory can actually be accessed directly without going through a sequence or going through other processes. And then we have random access, whereby each addressable location in memory has a unique physically wired addressing mechanism. The time to access given a location is constant, and the main memory and some cache systems are typically random access. So the good thing about random access is that any location can be selected at random. You don't have to follow the sequence, and directly addressed and accessed. Now, this seems like it is part of the direct access, but in reality, the random access is much more effective because the time given to access units of data is constant, whereas the direct access, the time is variable, because typically direct access combines direct access with sequential access. So this is why it could not provide the time constant. And then we have associate. A word is retrieved based on a portion of its contents rather than its address. So it is identified based on some of its data instead of its address. So each location has its own addressing mechanism, and whereby it is identified based on the portion of its data, and retrieval time is constant independent of its location or prior access pattern. So prior execution is not going to affect the associative accessing unit. And then cache memory may employ associative access. So the two most important characteristics of memory is obviously the capacity and also the performance. Capacity in the sense of how big is it, and in terms of performance, how fast is it. So there are 3 performance parameters that we can use to characterize the capacity and performance, which is the access time, latency, we have the memory cycle time, and also the transfer rate. So access time or latency, it is the time to execute the operation for a random access memory. And then for memory cycle time, it is the access time plus the additional time required before you move on to the next cycle. And then we have the transfer rate, the rate at which data can be transferred into or out of a memory unit. And for random access memory, that would be 1 over the cycle time. So these are all that we have talked about in previous lecture. I'm just going over them again. And then we have the memory. We have talked about the volatile versus the non-volatile. And we stopped here, the memory hierarchy. So before a processor designer can start designing, there are 3 questions that they ask themselves. Sorry, not processor, the memory designer. How much do we need? How fast should it be? And how expensive can it be? There is a trade-off among capacity, access time, and also cost. So the faster access time, it will cost you more per bit. The greater the capacity, it will cost you less cost per bit. It is like, you can imagine this like having a factory. If you are able to mass produce some clothes, then the price will drop. This is the same with memory. The greater the capacity, the smaller cost per bit. And then the greater the capacity, however, slowest the access time. You can also think of this in a way that if you try to manufacture clothes using a factory, then you would get more clothes at a lower price. However, you have to compensate in terms of its quality. Not compensate. You will get slower access time, or in your clothes example, your clothes would be of lesser quality compared to if it was handmade. Okay? So the way out of the memory dilemma is not to rely on a single memory component or technology, but to employ a memory hierarchy. So we typically combine fast and slow ones, and they are utilized for different purposes. So this is the memory hierarchy diagram. So you can see that going down, the pyramid is obviously getting wider, and at the top part, this is where we have our inboard memory, and then we have our outboard storage, and then we have our offline storage. So inboard memory such as registers, cache and main memory, and outboard storage, this one is outdated. We have others now. And then for offline storage, of course, this is also outdated. This is like 2016 text, I believe. As one goes down the hierarchy, the following occurs. So you would get decreasing cost per bit. Remember, if you have a factory, the cost goes down. Decreasing cost per bit. The higher the capacity, the greater the capacity, the lower cost per bit. And then as you go down, it is increasing in capacity. As you go down, it is increasing in access time. So the more clothes that you can produce, the lower quality is your clothes. So this causes increasing access time or slower access time. And then going down the hierarchy as well, you would see that decreasing frequency of access of the memory by the processor. What does this mean? Decreasing frequency. So for the top part, this is where the CPU interacts vigorously. Okay, vigorously is not the right word. Interacts more frequently compared to this guy over here. So the CPU and the processor and the memory over here will be like, okay, do you have it? No. Do you have it? No. Yes. Do you have it? Yes. They will be like communicating like that. Versus if this guy doesn't have what the processor need, then it goes to this guy, hey, do you have it? And then they will go and look around in their memory and say, oh, we have it. So they will return it. So compared to this guy and the outboard storage, the inboard memory will be in more frequency, will have a higher frequency of interaction with the processor versus the outboard storage. And then if the outboard storage does not have the data that the import memory is asking for, or the CPU is asking for, then the outboard storage would go to the offline storage and see if that is in the offline storage. So this one, very, very frequent. The processor with the outboard storage, less frequent. And then this is like super less frequent. So this is what it means by decreasing frequency of access. Everything goes through the first layer, second layer, and third layer. But I wouldn't call it layer. Let's just call it hierarchy. Okay, moving on. Okay, so cache and main memories. So here, let's take a look at this block diagram. We have two. The first one being the single cache. We have one cache over here, one CPU, and one main memory. And then for the 3-level cache organization, we have our CPU over here, we have a level 1 cache, we have a level 2 cache, and we have a level 3 cache, and then we have the main memory. So what does it mean? Why do we have the cache in between the CPU and the main memory? Like I mentioned to you before, the greater the capacity, the slower the access time, and also decreasing frequency, right? So the cache memory is designed to combine the memory access time of expensive high-speed memory combined with large memory size of less expensive lower speed memory. So this is what they are trying to do. So this is going to be faster than the main memory. The cache is going to be faster than the main memory. Of course, the cache is going to be more expensive because it's faster. The capacity is also going to be smaller. Whereas the capacity of the main memory is going to be bigger than the cache. It is going to be slower, but it is going to be less expensive. So you don't have to have multiple cache. You can combine the cache which is super fast with something that is not so fast, which is the main memory. So this is for a single cache. So between the cache and the main memory, the unit of transfer is blocks. And the unit of transfer between the CPU and the cache is going to be words. So let's look at this explanation. When the processor attempts to read a word of memory, a check is made to determine if the word is in the cache. If so, if the word is there, the word is delivered to the processor. If it is not in the cache, a block of main memory consisting of some fixed numbers of words is read into the cache, and then the word is delivered to the processor. Okay, so first the processor is asking, hey cache, do you have the data that I want to read? The cache is looking, it responds really fast. Oh, I don't have it, for example. And then the cache will transfer this request to the main memory. The main memory will respond by not giving the word that the CPU wants to read. However, it will transfer a whole entire block containing the word that the CPU wants to read. This is why the unit of transfer is block. And then the block is transferred to the cache. The cache goes through the block, and then we'll see what is the word that the CPU wants to read, and then it will return to the CPU with the data that it wants to read. So this is for a single cache. So what if the CPU asks the cache for a word to read and the cache has it because it already copied the data from the main memory? So the cache said, oh, I have it, let's see. So the cache returns the data that the CPU wants to read very fast. It doesn't have to go through the main memory. So the cache will store some of the data from the main memory, but not all of it. But if it does have the data that the processor wants, then it can respond really fast. Okay, so for a 3-level cache organization, the L2 cache is going to be slower than the L1 cache, and the L3 cache is going to be slower than the L2 cache. So the closer your cache is to the CPU, or the closer your memory is to the CPU, the faster your memory can respond. It is how it is designed anyway. So here we have a level 1 cache to be the fastest, level 2 to be fast, and level 3 to be less fast, and the slowest of all is the main memory. And then you would see that the level 2 cache is going to be bigger in capacity compared to level 1 cache, and level 3 cache is going to be bigger than level 2 cache, and of course the main memory is going to have the greatest capacity. Sorry, if you hear noises, that's not a ghost, it's my kid who is sick and I'm supposed to work from home right now. Okay, moving on. Okay, so we have the main memory structure today. So here is the cache structure, and this is the main memory structure. Of course, this is conceptually so that we can visualize things better. So for the cache, we can see that it has K words, which is the length of the block. And remember, we talked about how the main memory transfers data to the cache in the form of block, whereas the cache transfers memory to the processor. We have the processor. Wait, it's not working. In the form of words. So here, this is block length, which is composed of k words. And then we have the tag bit over here. And then we have line number. The line number goes from 0 to C minus 1. And then we have our memory structure. Our memory structure is composed of blocks. Block 0, block 1, block 2, up until block m minus 1. So we can see that the total number of blocks over here is m. Let me try again. Is m, and the number of lines that the cache has is small m. Okay, so this is the cache main memory structure. So we have our block over here, and this is our cache structure. So remember, we have talked about how the main memory transfers data in the form of blocks. The unit of transfer is block from the main memory to the cache. And the cache transfers data to the CPU or the processor in the form of words. So here you can see that the cache structure is composed of a tag and a block. But this is not it. This is not complete. But we will talk more on this later. So the memory will transfer its block to the cache, right? So one block is actually has all these data. Let's say it goes from 0 up until k words, and k words belongs to block number 0. And then another k words, a different k words will belong to block number 1, different k words will belong to block number 2, etc., etc. So let's say we are going to map block 0 onto one line in the cache. So the cache has a block length, which is the same, right? So this length is k. This is, let's just call this in parallel, but it will map it in the form of serial, like this. So you would get the same length of k, but in this k words in serial. Okay, so it maps it out like that. So the cache consists of m blocks called lines. So we have the line number, which goes from 0 up until c minus 1. But we will call the blocks as m, even though it's c over here. Each line contains k words plus a tag of a few bits. So the block length is actually the same as the block length of the main memory address. And then each line also includes control bits, not included over here, to indicate whether the line has been modified since being loaded into the cache. But this is not so important. The length of a line, not including tag and control bits, is the line size. So it's saying that the cache size is this entire thing, right? The cache size has a tag and control bit, a control bit and a tag, and then you have your length of line size. So you have line size, tag size, control size. And number of m lines is always going to be less than the number of capital M of the main memory, the number of blocks. Remember, the memory will always have a greater capacity compared to the cache. The cache has faster access, the memory has slower access. The capacity is different, the response time is also different. So at any time, some subset of the blocks of memory resides in lines in cache. For example, we have block 0, block 1, 2 mapped into the cache because the cache requested this data, so it is already there. So if a word in a block of memory is read, that block is transferred to one of the lines in the cache. So block 0 is mapped onto line number 0, block number 1 is mapped onto line number 1, etc. But because there are more blocks than lines, an individual line cannot be uniquely and permanently dedicated to a particular block. Because more blocks exist than lines, so you have more blocks, capital M, is more than small m. Thus, each line includes a tag that identifies which particular block is currently being stored. So the tag is usually a portion of the main memory address. So this is the function of the tag. Okay, let's move on. So we have more about the cache main memory structure. In referring to the basic unit of a cache, the term line is used rather than the term block for two reasons: to avoid confusion with the main memory block. They have the same length, but we are going to call them line. This is the same length, this is the same length, but one is called block, the other is called line. Because a cache line includes not only keywords of data, just as a main memory block, but also includes tag and control bits. So the cache structure is slightly different in the sense that it has the line size, tag, and also control. Now let's talk about the memory, the main memory. So the main memory consists of up to 2 to the power of n addressable words. 2 to the power of n addressable words. We will talk more on what this means. This memory is considered to consist of a number of fixed length blocks of k words each. So you have k words that make up one block. That is, there are m is the total number of blocks, and 2 to the n is the number of addressable words divided by k. So this would give you the number of blocks in the main memory. Okay, so main memory is 2n. One block is, the size of one block is k. So 2n divided by k would give you the number of blocks, which is 2n over k. Or you can just go over this one, which is capital M equals to 2 to the power of n over k. Now what is n? N is the total size of the memory, and k is the number of words per block. Okay? Alright, so we have gone through this one. Okay, so this is the cache read operation. First, we start off by receiving address. RA is read address. The processor generates the read address of a word to be read over here. So receive address, read address from CPU. And then is block containing read address in cache? First, it checks out with the cache. Do you have it? If the cache says yes, fetch the read address word and deliver to the CPU. If no, then the cache would access the main memory for block containing the read address. And then it would allocate a cache line for the main memory block. Remember, we had the cache over here and our main memory, and this is our CPU. This is our cache and this is our memory, main memory, MM. And this is our cache. This is H. Okay, so the CPU asks the cache, hey, do you have the read address that I want? The cache says yes. Okay, return or give the data that they want, the CPU wants. If the CPU asks the cache, hey, do you have the read address that I want? The cache looks over the lines that it has. Does it have the read address? No, so it would ask the main memory, hey, main memory, I don't have the read address that the CPU is asking for, so I want to copy your block. So the main memory does not give the read address, but it would give a block that has the read address. So the unit of transfer is block. And the cache said, okay, now I have it. The RA is now inside my cache. So now I can transfer the word that the CPU wants, or the read address that the CPU wants. So here we can see that two operations happen simultaneously, which is load main memory block from here to this, to the cache memory block into the cache line. It would map one block. Let's say this is block 0, and I would map it into, whoa, this is too thick. Map it onto line, let's say line number 20. That could happen. And then at the same time, the cache or the main memory will deliver the read address word to the CPU. Now, if the main memory transfers directly, then it would mean that it bypasses the cache. Now, if the cache transfers the word that is requested, then it means that the main memory cannot bypass the cache. So this depends on the organization structure of the cache. So let's see. So this is a typical cache organization. So we can see that the processor is here. We have a cache that is connected to the processor by the address line, the control line, and also the data line. And then we have an address buffer, and we also have a data buffer. And this address line, control line, and data line is connected to a system bus, which is connected to the connected to the main memory. So here, when a cache hit occurs, a cache hit means that when the CPU requests read from cache, the cache has it. This is what cache hit means. And then we have another term which is cache miss. When the CPU asks a read from a cache and the cache does not have the read address that the CPU wants, then this is considered to be a cache miss. Now, in a cache hit, the data and address buffers are disabled. So when the CPU asks the cache, do you have what I want? The cache says yes. Immediately when the cache says yes, then these guys would be disabled, which means that there would be no traveling towards the main memory. It's blocked. That is what it means when it is disabled. So communication is only between the processor and the cache with no system bus traffic. So you are minimizing traffic because you are disabling the system bus or the address buffer and data buffer. And then when a cache miss occurs, which means that the CPU is asking the cache, hey, do you have what I want? The cache says no. Therefore, the cache has to ask the system bus, or like to ask the main memory. The desired address is loaded onto the system bus over here. Let's remove this one first. So it would have to load the address to the address buffer, and the data are returned through the data buffer. So it would ask from the main memory directly, and the main memory would supply the data to the data buffer, and the data buffer would transfer this to the CPU. In other organizations, the cache is physically interposed between the processor and main memory for all data, address, and control line. Now, in this case, we could see that the main memory can bypass the processor can bypass the cache if a cache hit occurs. If the cache does not have what it wants, hey, I just want to go to the main memory and ask myself. So this is when the cache is not physically interposed. Now, another type of organization of the cache would be the cache is physically interposed between the main memory and processor, which means that everything has to go through the cache. Now, these are the two different types of organization. So, CPU asks cache, hey cache, do you have it? Yes, so it returns the read address that the processor wants. The processor asks again, hey, do you have what I want? The cache says no. The cache will ask the main memory through the system bus, and the main memory will supply that data to the cache, and then the cache will supply it to the processor. So those are two different organizations. So these are the elements of cache design. So we would have logical versus physical. We will talk more on what this is. We will talk on cache size, and we will talk on mapping function, whereby we will see that the cache can be mapped using direct function, associative function, and set associative function. And then we have replacement algorithm, which is LRU, FIFO, and LFU. And then we have some write policy, which is write through, write back. And then we have line size, number of caches, single or two level, unified or split. So let's talk more on this. So for cache address, let's talk about the virtual memory first, or logical. So virtual memory is facility that allows programs to address memory from a logical point of view, without regard to the amount of main memory physically available. Now the name is virtual, which means that it is making an address that sometimes can be the same place or sometimes does not exist. This is what virtual means, right? So it is a facility that allows programs to address memory from a logical point of view, because this is what the program needs at that point in time, but it does not consider whether that memory is physically available or not, hence the name virtual. When used, the address fields of machine instructions contain virtual address. For reads and writes from main memory, a hardware memory management unit called MMU translates the virtual address into physical address in the main memory. Okay, so this is logical and physical cache. So here we have a processor. We have our cache over here connected to a logical address line connected to the MMU, which translates the virtual address to the physical address in the main memory. Main memory is also connected to the cache and the processor via a data line. And then for the physical cache, we would have a processor, a logical address that is connected to an MMU, which translates the virtual or logical address to become the physical address in the main memory. Now the cache is connected to the physical address, and the cache is also connected to the main memory and also to the data line that is connected to the processor. So the difference is where the cache is located. For the physical cache, the cache is located at the physical address, and for the logical cache, the cache is located at the logical address. So the difference between the logical virtual cache versus the physical cache. So for the virtual cache, we have talked about how it stores data using virtual addresses. Sometimes that physical address might not be there. The processor accesses the cache directly without going through the MMU, which we have seen here. The processor accesses the cache without going through the MMU. Therefore, the access speed is faster than physical cache because the cache responds before the MMU can do any translation. However, the cons would be the supply each application with the same virtual address if the programs supply each application with the same virtual address space. Thus, the same virtual address can actually refer to two different physical addresses. So let's say I am allocating this program with a virtual address called A, and this program with the same virtual address A. However, in the main memory, this would be block 0, and for this guy, this would be block 1 in the main memory. For example, even though they have the same virtual address, they could mean different physical addresses in different blocks. So this is the cons of the virtual cache. And again, because the cache is situated next to the processor can directly access the cache without going through the MMU. And for the physical cache, the processor has to go through the MMU before it can access the cache. So the access time is slower. Okay, so these are the processors and the types. Year of introduction, very outdated. And this is L1 cache, L2 cache, L3 cache. And we know that L3 cache is supposed to have a greater capacity than L2, and L2 is supposed to have a greater capacity than L1. L3 is supposed to be slower than L2, L2 is supposed to be slower than L1. So let's see if that is really the case. So let's see, this is 16. Let's find out. Okay, so let's look at this line. So we have a 32 kilobyte L1 cache, 256 kilobyte L2 cache, which is greater, and then you have a 2 megabyte L3 cache, which is greater in capacity. Okay, so this is the capacity of, the size of the cache depending on the level. So these are the current cache. That table was the outdated one. So these are current caches that you can find. This is, let's see, AMD's Ryzen 5 5600X has a 384 kilobyte L1 cache, a 3 megabyte L2 cache, and a 32 megabyte L3 cache. Now this is quite fast considering 32 megabyte is quite big. So you can refer more to this link if you want to read more on the AMD Ryzen 5 5600X. And then here we can see that this is the size of the L1, L2, L3 cache of the Intel Core i5-3570K CPU. So let us zoom a bit on this one. So here we can see that we have L1D and L1I cache. So these are two L1, but they are separated into two for a better performance. So the L1 is divided into the L1D and L1I, whereby the L1D cache is 32 kilobyte and the L1I cache is 32 kilobyte as well. And then you have your L2, which is 256 kilobytes, and your L3, which is 6 megabytes. So this guy is greater than the L2, this guy is greater than the L1, even though we have two L1s over here. So a general rule of thumb that we can follow in designing memory or cache is that the L1 memory cache is typically 100 times faster than your random access memory, while the L2 cache is around 25 times faster. Okay? So here, this is the Intel next generation microarchitecture. I don't remember what structure this belongs to, but let's go over it. So here we can see that the L1 cache is divided into the L1D and L1I, which is what we saw over here. And then we can see that the L1 is connected to the L2 and the L2 is connected to the LLC or the L3 last level cache, which is a 2 megabyte per core. Then for the other core, you have your L1 level, your L2 level, and connected to your L3 level core. And then your level 3 core is connected to your graphic cache. And then your L3 cache is connected to a system agent, connected to a PCI Express, connected to other devices that you wish to connect to. And your alright, so I'm clicking on the link AMD Ryzen 5 5600X desktop processor. So we see that, let's go for the performance. Okay, here we have it. So these are the general specifications. The number of CPU cores that this Ryzen has is 6. Number of threads is 12. We have not talked about threads yet. And then it has a maximum boost clock of 4.6 gigahertz, which means that it's quite fast. Then its base clock, which is 3.7 gigahertz. And then its L2 cache is 3 megabyte. L3 cache is 32 megabyte. And then we have our what else have we learned? The connectivity is PCI Express version 4.0. The one that we talked about in the slide is PCI Express 3.0. So this is a high level. And then the system memory type is double data rate 4th generation. And the system memory specification is up to 3200 megahertz. So what are the other things that we have seen? So partially, we can already read the specifications of our processor, right? So I'm excited to learn more, to teach more, and hopefully by the end of our class, we will know exactly what everything means in the specification, okay? So let's talk about the mapping function of the cache with the memory. Because there are fewer cache lines than the main memory blocks, an algorithm is needed for mapping main memory blocks into cache line. We have seen that the cache line is fewer than the main memory. Main memory was indicated by capital M, if you guys still remember. And then for the cache line, the total number of lines is M. M is considerably smaller than capital M. So 3 techniques of mapping from main memory to cache can be used, which is the direct, associative, and set associative. We will look into some math problems for these mapping functions. So we'll see practice problems in a bit. So the first technique is called the direct. It is the simplest technique. it maps each block of main memory onto only one possible cache line. And then we have the associative, permits each memory block to be loaded into any line of the cache. The cache control logic interprets a memory address simply as a tag and a word field. We will see what this tag and what this word field is. We have briefly seen the structure of cache line, right? But we have not talked more on it. We will do so later. To determine whether a block is in the cache control logic must simultaneously examine every line's tag for a match. So the tag must be quite small for this examining process to happen fast. And then we have the set associative, which is more currently employed these days, a compromise that exhibits the strength of both direct and associative approaches while reducing their advantages. So set associative is a combination of direct and associative that minimizes the disadvantages of both functions. Okay, so these are two direct mapping techniques, which is the first one, which is direct mapping, and the second one is associative mapping. Let's talk about direct mapping first. So here your main memory is situated over here. Previously your main memory was over here. That's fine. It's just a change in position. So this is your memory. You have your first M blocks of main memory. So this is block 0, block 1, block 2, block 3, up until block M-1. So this length of your block is one word, and it is also called B. And then we have our cache memory. This line size is going to be the same size as your block length. This is block size. This is block length. So B is length of block in bits, and T is length of tag in bits. So you would see that this line size is the same length as the length of block in bits, and T is the tag in bits, which is not related in any way or in any shape or form to the main memory. For the cache, you would have M lines. For the main memory, you would have capital M number of blocks. Okay. So for associative mapping, you have one block of main memory. This is only one block. We're taking one block. Let's say it's B0. And this B0 block can be mapped onto anywhere or in the cache memory. Can be mapped onto any line. This is in contrast to the direct mapping, whereby this has to happen in order. This guy, no order. Any line is fine. So let's continue for direct mapping, cache organization and calculation in the next lecture. So I'll see you there. Bye for now.